For as long as humans have looked up at the night sky, the moon has been our oldest companion, steady, familiar, quietly orbiting above us. But there is a truth most people never consider. We never see the moon the way it truly is, not completely. Every night, we stare at the same face, its craters, its seas of basalt, its scars from ancient impacts. Yet on the far side, permanently hidden from Earth, lies another world entirely. A world of jagged mountains, deep basins, fractured crust. A world shaped by forces we did not understand until the modern space age. A world we did not see until 1959. A world no human eye had ever witnessed in the entire history of our species. And the deeper question is not why it is hidden, but what has happened there while it remained out of sight. The far side of the moon is more than a direction. It is a geological divide, a cosmic mystery, and perhaps the most dramatic example of how celestial mechanics can sculpt two different worlds on the same body. Why does one hemisphere look smooth and dark, while the other is violently cratered and ancient? Why is the crust thicker on the side that never faces us? Why did the Maria, the vast basalt plains, form only where we can see them? And what does that reveal about Earth's earliest days, when both worlds were still molten? Tonight, we'll enter the unseen hemisphere, not the one poets wrote about, but the one shaped by physics, impacts, magnetism, tidal locking, and billions of years of silent evolution. This is the story of the moon's hidden face, a face the Earth will never see, but one that tells the real history of our celestial companion. Now, let's begin. Chapter 1: A world forever turned away. For as long as humans have looked at the sky, the moon has been a familiar presence, steady, unchanging, a half-lit companion, suspended above Earth's horizon. Yet what we see from our world is only one face of a much larger and more complex reality. The opposite hemisphere, the far side of the moon, remained unseen for millions of years of human history. It was myth, speculation, imagination, and mystery long before it became data, geology, and science. The reason the far side stayed hidden is simple yet extraordinary: tidal locking. For billions of years, gravitational interactions between Earth and the moon gradually slowed the moon's rotation until its spin period matched its orbital period. The result is a celestial equilibrium where the moon rotates just fast enough to keep the same face turned toward Earth at all times. It is not the moon that refuses to show us its secrets, it is gravity that holds the silence in place. But what lies on that unseen hemisphere is not merely a mirror of the near side. In fact, the far side is geologically different in ways that are profound. While the near side contains the familiar Maria, the dark, basaltic plains that form the shapes ancient cultures interpreted as rabbits, crabs, or faces, the far side is dominated by highlands, bright and densely cratered terrain, almost unchanged since the early solar system. These regions hold some of the oldest accessible surfaces anywhere in our planetary neighborhood. Why such an asymmetry? Why is one side filled with volcanic plains and the other covered in cratered, primordial crust? The answer lies in the moon's internal structure, its thermal history, and the strange imbalance that developed during its early formation. Measurements from missions like Lunar Prospector, Kaguya, and Grail reveal that the moon's crust is significantly thicker on the far side, up to 15-20 kilometers thicker in some regions. A thicker crust prevented magma from reaching the surface, so the far side never flooded with basaltic lava as the near side did. As we explore the far side, we also encounter one of the most dramatic features in the solar system, the South Pole Aitken Basin, a colossal scar stretching 2,500 kilometers across and plunging more than 8 kilometers deep. It is one of the largest and oldest impact basins ever discovered, so immense that it deforms the Moon's overall gravitational field. The basin may expose material from the lunar mantle, offering clues to how the Moon cooled, differentiated, and evolved after its violent birth. Yet for centuries, everything beyond the Moon's visible limb was unreachable. No telescope, no matter how powerful, could see it. The far side is permanently shielded from Earth's radio signals, making it the quietest radio environment anywhere near our planet. Explorers dreamed of what might be there, but no human eye saw it until 1959, when the Soviet spacecraft Lunar 3 transmitted the first grainy images of a landscape alien to everything known. Those images changed the story of the Moon forever. We learned that the hemisphere we know is the exception, not the rule. The far side told a different history, a raw, ancient record of bombardment preserved in stone. In this chapter, we establish the first truth. The far side of the Moon is not simply what Earth never sees, it is what Earth never shaped. The side we look at nightly was molded by tidal forces, internal heat, and thin crust. The side forever turned away remained untouched, thick, ancient, and cold. Understanding this duality is essential because everything we thought we knew about the Moon, its origins, its evolution, its internal structure changes when seen through the geological and gravitational asymmetry between its two hemispheres. And as we step from this foundation into the next chapter, we move deeper into the story hidden within the Moon's unseen face. Not just what it looks like, but why it became so different. Chapter 2, Why We Never See the Far Side. If Chapter 1 revealed how the Moon first formed, then Chapter 2 begins with a question that has followed humanity for thousands of years. Why does the Moon always show the same face? Why is one hemisphere locked in eternal familiar light, while the other remains a world Earth-bound observers never witness directly? To understand this mystery, we must look at orbital mechanics, tidal forces, and the subtle friction that has shaped the Moon's behavior over billions of years. The dark side is not truly dark, it receives sunlight just as often as the near side, yet it is forever hidden from Earth because of a physical process called tidal locking. And this phenomenon isn't merely a coincidence, it is a predictable outcome of gravitational physics and one of the most widespread behaviors among moons in the solar system. 1. Gravity's grip, the beginning of tidal locking. Shortly after the Moon formed from Earth's debris disk, it orbited the young planet much closer than it does today, possibly as close as 25,000, 30,000 kilometers. At this distance, Earth's gravity was immensely powerful, so powerful, in fact, that it created tidal bulges on the Moon, slight stretches of the lunar surface caused by the difference between gravitational pull on the near side versus the far side. These bulges did not point exactly toward Earth at first. Because the newborn Moon was spinning rapidly, the tidal bulges lagged behind its rotation, creating a twisting force, a torque that slowly acted like a cosmic brake. This is the essence of tidal locking. Rotation slows, bulges realign, rotation slows more, until the Moon becomes synchronized with Earth. The process didn't take long in cosmic terms. Calculations suggest the Moon may have locked its rotation within the first 100 million years of its existence. Once locked, it remained so permanently, presenting one hemisphere toward Earth and rotating just fast enough to keep the same face pointed at us during each orbit. This is why one side of the moon, the one we see, became the near side, while the opposite hemisphere became the far side. 2. The far side isn't dark, just hidden. One of the most persistent misconceptions in astronomy is that the far side of the moon lives in perpetual shadow. In reality, the sun illuminates it for half of every lunar cycle. Daylight sweeps across the far side just as it does across the near side. The difference lies not in sunlight, but in visibility. Earth never has a direct line of sight with the moon's far hemisphere. If the moon rotated faster, we would eventually see all of it. If it rotated slower, we would see even less than half. But tidal locking has tuned its rotation to the precise rate that forever hides the far side from Earth. Only spacecraft beginning with the Soviet Lunar 3 mission in 1959 have shown us what it looks like, and what they revealed was completely unexpected. 3. A hemisphere unlike the moon we know. When Lunar 3 transmitted the first blurry photographs, scientists saw a lunar landscape radically different from the familiar near side. The far side was almost entirely covered in cratered highlands, nearly devoid of maria, the dark volcanic plains that dominate the near side, thicker in crust, and far more rugged. This raised a new question. Why are the moon's two hemispheres so different? The answer lies partly in how the moon cooled and partly in how Earth influenced its early geology. After its formation, the moon's near side faced Earth's molten, hot surface. Earth's infrared radiation, essentially heat, acted like a thermal lamp, warming the moon's near hemisphere. Meanwhile, the far side cooled faster in the absence of Earthshine. Because of this difference, the crust on the far side solidified thicker. Later, when the moon experienced enormous asteroid impacts that formed large basins like Imbrium and Serenitatis, molten material welled up to fill these basins on the near side, creating the dark maria. The far side, with its thick crust, did not melt through. Its impact basins remained bright and heavily cratered. It became a fossil of ancient bombardment. Thus, the far side is not just hidden from Earth, it is fundamentally alien, a different geological world glued to the familiar moon we see each night. 4. Librations, the slight wobble that lets us peek beyond the edge. Though tidal locking prevents the moon from rotating freely, the moon does not keep a perfectly consistent orientation. Small oscillations called librations allow Earth observers to see slightly more than half of the lunar surface, roughly 59%, not 50%. There are 3 types of libration. 1. Libration in longitude, caused by the moon's elliptical orbit. When it moves faster or slower along the orbit, we see a bit around the eastern or western edge. 2. Libration in latitude, caused by the moon's axis being slightly tilted relative to its orbital plane. This lets us glimpse slightly over the north and south poles. 3. Diurnal libration, caused by the observer's position on Earth. At moonrise and moonset, the moon appears at a slight angle. Together, these subtle motions let us peek about 9% extra around the edges, but the true far side remains invisible without spacecraft. 5. Why tidal locking is common in the solar system. The moon is not unique. Tidal locking is the rule, not the exception. Examples include Jupiter's moons Io, Europa, Ganymede, and Callisto all show the same face to Jupiter. Saturn's moons, including Titan, Enceladus, and Tethys, Pluto and Charon, tidally locked to each other, forming a synchronized binary world. Many exoplanets orbiting close to their stars. Tidal locking stabilizes orbits and dissipates rotational energy. Over time, gravitational systems tend naturally toward energy-efficient configurations. A locked moon is simply the most stable long-term state. Thus, the moon is not doing anything unusual, it is obeying a universal gravitational pattern. 6. What if the moon were not locked? If the moon rotated independently, Earth would see shifting Maria patterns, volcanic plains sweeping into view, and occasionally the jagged highlands of the far side rising over the horizon. Human cultures assigned mythology to the unchanging face of the moon precisely because it did not rotate relative to Earth. A rotating moon might never have inspired the same folklore, spiritual imagery, or symbolism. Tidal locking shaped not only the moon, but human imagination. 7. A hidden hemisphere with a future role. The far side of the moon is not just a geological curiosity, it is scientifically invaluable. It is radio silent, shielded from Earth's electromagnetic emissions, making it the best place for radio telescopes to study the early universe. Its thicker crust preserves a purer record of ancient impacts. Its permanently shadowed craters may contain pristine ice, a resource for future exploration. The side we never see could become the most important side for science. Chapter 3: A Locked Dance. Why the Moon Never Turns. If Chapter 2 revealed how the moon's far side was sculpted by violent impacts and a different internal composition, then Chapter 3 brings us to a more subtle, almost mathematical mystery. Why has no human on Earth ever seen this hemisphere with their naked eyes? Why does the moon keep one face toward us, as if performing a dance choreographed with perfect precision? To understand this, we must go deeper into orbital mechanics, tidal forces, and the strange way gravity can reshape the behavior of entire worlds. 1. The physics of tidal locking. The moon did not always show us only one face. Billions of years ago, shortly after its formation, the moon spun much faster, completing a rotation in just a few hours. Its days were short, its rotation free, its surface turning through space without pattern or restraint. But Earth pulled on it. Like a hand gripping a spinning wheel, Earth's gravity generated tidal bulges, elongated stretches of lunar rock displaced slightly by gravitational forces. Over time, friction inside the moon acted like a cosmic brake. Rotation slowed, the bulges aligned, and eventually, the moon's rotational period matched its orbital period. This is tidal locking, the gravitational synchronization between two bodies. When a smaller object rotates at exactly the same rate it orbits, it is not a coincidence. It is the natural fate of moons. It is why Jupiter's moons are locked, why Pluto and Charon are mutually locked, why nearly every large moon in the solar system shares this destiny. The moon's far side is hidden not because it is distant, but because gravity has choreographed a dance so balanced and ancient that breaking it now would require unimaginable force. 2. The libration, illusion, why we see more than 50%. And yet, oddly, humans can see more than half the moon's surface, about 59%. In fact, this is due to libration, a gentle wobble caused by the moon's elliptical orbit, its tilted rotational axis, slight variations in velocity as it moves around Earth, These wobbles allow Earth-based observers to peer a little around the edges, first one side, then the other, revealing slivers of terrain normally hidden. This is why certain lunar features near the edges appear in and out of view over months. Not because the moon rotates freely, but because its orbit rocks it slightly, like a ship rolling on a slow tide. But even with libration, the far side remains permanently hidden. Everything beyond the line of sight, the hemisphere facing away, anchored in darkness from our vantage point, never rises above the lunar horizon. No telescope from Earth can see it. No astronaut has seen it with their own eyes without traveling to the other side. The dance remains perfectly synchronized. 3. How gravity sculpted both worlds. Tidal locking also linked Earth and the moon in deeper, subtler ways. Because the moon slowed down, Earth also slowed down. Our planet used to spin faster, much faster. A day on early Earth may have been only 6 hours long, but the same tidal interaction that braked the moon's rotation also stole momentum from Earth's spin, transferring it into the moon's orbit. So, Earth's rotation slowed, lengthening our days. The moon drifted outward, moving 3.8 centimeters farther away each year. This is not poetry, it is angular momentum transfer, written into the tides of our oceans and the recession of the moon. Every high tide is a reminder of the gravitational conversation between Earth and its satellite. Every lengthened day is a whisper from the moon, saying, "I am still shaping you." And every centimeter that the moon drifts away is the echo of an ancient braking mechanism that still operates today. 4. Why the far side is geologically different. Tidal locking also had profound geological consequences. The near side, the face that always looks toward Earth, is thinner, more volcanic, dominated by mare, the dark basaltic plains that paint the moon's most familiar features. The far side is thicker, heavily cratered, more rigid, with far fewer volcanic regions. There are several scientific explanations for this hemispheric asymmetry. A. Earthshine heating. In the early molten era, Earth glowed red-hot thousands of degrees after the giant impact that formed the moon. This radiated heat toward the near side, slowing its cooling. The far side cooled faster, forming a thicker crust. B. Tidal heating. Constant tidal flexing warmed the near side more. C. Interior distribution of radioactive elements. Some heat-producing elements, like thorium and potassium, concentrated more on the near side than the far side. These differences shaped two worlds in one, a near side sculpted by heat and volcanism, and a far side fossilized in ancient collisions. Thus, the moon does not simply look different on the other side. It is different, fundamentally, structurally, geologically. It is a world Earth never sees, but a world shaped by Earth's own influence. 5. Why humans obsess over the hidden side. There is something profound about the far side. It is not darker, it is not colder, it is not mysterious in a supernatural sense, but it is hidden, completely and permanently from Earth. That alone stirs imagination. We are wired to be drawn to the unseen, to want to explore the quiet places that lie beyond our horizon. The far side of the moon is not just a hemisphere. It is a symbol of curiosity, mystery, and the unfinished work of exploration. Every culture, every era, every scientific generation has looked up and wondered, what is on the other side? And the answer, as we continue to learn, is as scientific as it is poetic. Another world silent, ancient, untouched by human eyes for billions of years. Chapter 4: The Tidal Prison: Why the Moon Can Never Turn Toward Us. For as long as humans have looked upward, the Moon has shown only one face, its familiar near side, marked by dark volcanic plains and bright crater-studded highlands. It rises and sets with the same expression every night, as if frozen in eternal stillness. But behind that stillness lies one of the most fundamental dynamical interactions in the solar system: tidal locking, a precise, mathematical prison created by gravity itself. Understanding why the Moon forever hides its far side requires stepping back to a time when neither Earth nor the Moon looked anything like they do today. A world still glowing, the early, hot Moon. After the cataclysmic impact that formed the Moon described in the previous chapter, our satellite was not a serene white orb in a quiet sky. It was a molten world, glowing red with heat, its surface a global magma ocean. Earth was still reshaping itself, and the distance between the two bodies was dramatically smaller. In those early eons, the Moon rotated much faster than it does now. Each rotation produced enormous tidal bulges raised not in water, but in solid rock, flexed by Earth's gravitational pull. This tidal flexing produced friction deep inside the Moon's mantle, turning rotational energy into heat. And heat, as it always does, needed somewhere to go. Through the slow bleeding of that energy, the Moon's rotation began to decrease. The process was glacially slow, but relentless, like invisible brakes applied over millions of years. Eventually, the Moon reached a perfect equilibrium. It rotated once on its axis in exactly the same amount of time it took to orbit Earth. This is tidal locking, gravity's hand, the mathematics of a frozen rotation. To understand why tidal locking is so stable, imagine the Moon's crust as slightly elongated, a subtle oval shape caused by Earth's gravity tugging more strongly on the near side than the far side. As long as this gravitational elongation points toward Earth, the system remains calm. But if the Moon were to rotate even a few degrees ahead or behind, Earth's gravity would pull on the bulge and snap it back into alignment just like a stretched spring. This gravitational restoring force ensures that the Moon's rotation can't drift. No external torque can twist it into a new orientation, and its far side will remain hidden indefinitely. It is not simply that the Moon doesn't turn, it is that the laws of orbital dynamics do not allow it to. The far side versus the near side, a planetary mismatch. What makes this phenomenon even more fascinating is that the Moon's internal structure contributes to its locked orientation. The near side is thinner and contains large basaltic plains known as lunar maria, formed by ancient volcanic upwellings. The far side, by contrast, has a crust significantly thicker, up to 50 kilometers thicker, and is dominated by rugged highlands. This asymmetry shifts the Moon's internal mass distribution. The heavier, denser regions lie slightly closer to Earth's direction, further reinforcing the locked orientation. In other words, the Moon's own geology participates in its captivity. The Moon is not just tidally locked because of gravity, it is tidally locked because its entire body has reshaped to make any other orientation impossible. Libration, the Moon's subtle wobble. Although the far side never fully rotates into view, the Moon does perform a gentle wobbling motion called libration, caused by the ellipticity of its orbit, its slight axial tilt, and variations in orbital speed. Thanks to libration, Earth-based observers can see about 59% of the lunar surface over time, not just the exactly 50% one might assume, but the remaining 41%, the true far side, remains forever out of sight. Even with libration, no human being on Earth has ever looked upon the far side with the naked eye. It was only in 1959 that the Soviet spacecraft Lunar 3 transmitted the first images, showing a world dramatically different from the near side, heavily cratered, lacking the vast dark plains that define the face we know. The long-term future: will the moon always stay locked? Tidal locking is not just a current state, it is the moon's evolutionary endpoint for billions of years, and possibly forever, unless an enormous gravitational disruption occurs. The system is so stable that the moon slowly drifts 3.8 centimeters farther from Earth each year. Its orbital period increases, but the rotational lock remains unchanged. Eventually, far beyond human timescales, tidal effects will also slow Earth's rotation until one Earth day matches one lunar month. In that distant epoch, Earth and Moon will be mutually locked, each showing only one face to the other. Humanity will be gone long before this happens, but the gravitational choreography will continue. Why this matters for what Earth never sees. Tidal locking is not just a celestial curiosity, it is the reason. The far side has a radically different landscape. Enormous impact basins formed without being visible to Earth. Future radio telescopes may be placed there, shielded from Earth's noise. Theories about ancient volcanic flows and crustal thickness exist, and why the moon has become an archive of early solar system history. Because one hemisphere faces eternal daylight from Earth's oceans and continents, while the other faces unbroken darkness, the moon became two different worlds. The near side tells one story, the far side tells another, and Earth, locked into its perpetual viewing angle, receives only half the tale. Chapter 5: The Hidden Border, where sunlight ends and shadow begins. For billions of years, the moon has presented the same face to Earth, locked by tidal forces into a perfect rhythmic orbit. But this visible hemisphere is only half of the lunar experience. To understand the true nature of the moon, scientists must examine a boundary far more fascinating than a simple line between light and dark: the terminator, the shifting frontier between daytime and night. This boundary is not static. It crawls across the surface every lunar day, reshaping temperatures, shadows, and the physics of the terrain. And nowhere is this transformation more dramatic than at the edge of the dark side. The terminator is where sunlight dies. It is a transition zone only a few kilometers wide, yet the physical behavior of the lunar surface changes in ways that are both extreme and scientifically revealing. Temperatures swing wildly from searing 120 degrees Celsius under the sun to bone-cold 170 degrees Celsius in the darkness. This is a territory where rock shrinks within minutes, where dust levitates, where shadows stretch into nearly infinite lengths. The moon lacks atmosphere, and thus lacks the gradual softening of sunrise or sunset familiar on Earth. Light appears suddenly, shadows collapse instantly, heat rises violently through rock. The terminator is the closest thing the moon has to weather, a daily mechanical stress event that has been sculpting its surface for eons. For the far side, this frontier is especially important. The side facing away from Earth experiences some of the most severe temperature gradients because it lacks the moderating infrared radiation. Earth reflects onto the near side. Infrared earthshine, which subtly warms the Earth-facing hemisphere, never touches the far side. This means the terminator there is colder, harsher, and far more extreme. When dawn reaches the far side after 14 days of darkness, sunlight slams into stone that has contracted to its coldest possible state. The sudden expansion fractures boulders, weakens crater rims, and drives a slow but constant mechanical process known as thermal fatigue, the moon's quiet, relentless erosion engine. Unlike Earth, where water and wind dominate erosion, the moon's landscape is reshaped almost entirely by thermal stress and micrometeorite bombardment. Every sunrise on the far side becomes a geological chisel. The heating of the surface produces stresses strong enough to split rocks the size of small buildings. Over millions of cycles, this process creates the sharp, angular, regolith grains sampled during the Apollo missions. The dust on the moon, abrasive, glass-sharp, electrostatically active, owes much of its character to the violent transitions at the terminator. The dark side experiences these transitions with greater severity than anywhere else on the lunar surface. At this boundary, another phenomenon emerges: the mysterious movement of dust. Lunar dust is notoriously troublesome. It clings to spacesuits, interferes with instruments, and behaves in ways that defy intuition. One of the most puzzling behaviors occurs precisely at the terminator: electrostatic lofting. As sunlight fades, the electric charge of the surface shifts abruptly. The ultraviolet radiation that charges the daylit surface shuts off instantly, while the dark side remains negatively charged due to solar wind electrons. This steep electrical gradient can create forces strong enough to lift dust grains several centimeters, even meters above the ground. Apollo astronauts reported horizon glow, a soft, shimmering light seen just before sunrise or after sunset, possibly caused by charged dust suspended along the terminator. On the far side, where Earth is never visible and no atmospheric ionization leaks through from below, these electrical changes may be even stronger. Recent models suggest that the far side terminator may produce taller, denser dust plumes. These structures could influence radio observations, surface chemistry, and the stability of future far-side bases. When China's Chang'e 4 lander touched down in 2019, the first spacecraft in history to land on the far side, its instruments began monitoring how dust behaves during the lunar dawn. Early readings hinted at unusual electrical behavior unmatched by anything recorded on the near side. The far side terminator may be one of the most electrically active surfaces in the solar system for its size. This region also reveals something deeper about the moon's interior. Heat flow measurements from Apollo and later missions show that the moon's crust is thicker on the far side, up to 20 kilometers thicker in some regions. This asymmetry affects how sunlight warms the surface and how heat dissipates after nightfall. A thicker crust means slower heat transfer, contributing to the cold, unyielding nature of the far side night. When dawn eventually arrives, the surface must absorb sunlight rapidly, driving even more intense thermal cracking. In this way, the terminator becomes a probe, a natural scanner, exposing how the moon's crust responds to energy. The terminator also shapes how we see the moon from Earth. The near side's familiar craters and Maria, the vast, dark volcanic plains, exist largely because ancient impacts and magma activity were more common on that hemisphere. But the far side is different, heavily cratered, rougher, riddled with ancient scars. The terminator sweeps across these features like a spotlight, revealing and concealing them every lunar day. Scientists use terminator lighting to map topography with exquisite detail. Long shadows exaggerate slight rises in terrain, turning small ridges into towering silhouettes. Before spacecraft provided direct images of the far side, researchers used subtle variations in the terminator's motion to infer the moon's shape and wobble, the phenomenon known as libration. Today, we know that libration occasionally allows Earth to glimpse slightly beyond the near side, but never enough to reveal the full far side. Only spacecraft can. And yet, even with modern imaging, the terminator remains essential. NASA's Lunar Reconnaissance Orbiter takes images at multiple sun angles precisely because the terminator's shadows reveal surface textures invisible under full illumination. The terminator is also where many future missions will focus. The temperature extremes and electrical environment provide a stress test for rovers, habitats, and power systems. Dust lofting could affect telescopes stationed on the far side. And if humanity ever builds a radio-quiet observatory in the South Pole Aitken Basin, one of the most promising locations in the solar system for studying the early universe, understanding the behavior of the terminator will be crucial. In the dark side narrative, the terminator is not simply a boundary between light and night. It is a dynamic frontier, an ever-moving agent that sculpts landscapes, fractures stone, electrifies dust, and reveals the machinery of the moon's internal structure. It is the line that divides what Earth can see from what Earth can never see, and it is the gateway to everything that makes the far side a world of its own. As we leave the terminator behind, the next chapter will take us deeper into the geology and violent history that shaped the far side's unique surface, a landscape unseen for all of human history until spacecraft finally unveiled its true face. Chapter 6: The Lunar Far Side, a world without Earthlight. If the near side of the moon is defined by the soft blue glow of Earth hanging permanently in its sky, then the far side is defined by the absolute absence of it. When you cross the imaginary boundary between the hemisphere we know and the hemisphere we never see, it feels less like moving across a landscape and more like stepping into a different category of world. In Chapter 5, we explored why synchronous rotation locks one hemisphere toward us forever. Now, as we follow that logic to its natural conclusion, we arrive at a frontier that has captivated astronomers for decades: the far side, the hemisphere that has lived in perpetual earthlessness for billions of years. And its story is stranger, deeper, and more revealing than anything on the near side. A hemisphere without Earth. The most fundamental difference between the two sides of the moon is visual, immediate, and profound. From the far side, Earth is never visible, not once, not ever. For any observer standing there, Earth is not an object that occasionally rises or sets. It is simply missing from the sky entirely, the way a star that never formed would be missing. This absence has consequences that extend far beyond aesthetics. Earth is not only a bright object, it is the brightest object in the lunar sky. Its reflected sunlight is dozens of times brighter than the full moon we see from Earth. It bathes the near side in a constant source of Earthlight, subtly shaping thermal cycles, influencing surface cooling, and contributing to the near side's very different geological signature. The far side, deprived of this illumination for 4.5 billion years, cooled differently, fractured differently, and evolved along a path that no longer resembles the face we know. A dramatic geological contrast. When the Soviet spacecraft Lunar 3 sent back the first images of the far side in 1959, scientists were stunned. The hemispheres are so different that they barely look like parts of the same moon. The near side is dominated by maria, the dark basalt plains that fill enormous impact basins. But the far side? Almost none. Instead, the far side is a world of cratered highlands, heavily battered, rugged, and ancient. But why would only one side of the moon be flooded by volcanic basalt? This is where Earth's invisible influence becomes unmistakable. Scientists believe that when the moon was young and molten, Earth's gravity created tidal asymmetry, a difference in heat retention between the two hemispheres. The near side's crust remained thinner, allowing magma to erupt and fill basins. The far side's crust cooled thicker, harder, and far less forgiving. The result? Near side, smooth volcanic plains. Far side, heavily cratered mountainous crust. The entire face of the moon we never see is a geological archive of impacts so ancient that many predate Earth's oldest surviving rocks. A radio silence found nowhere else. But the far side holds another quality, one that makes it unique not only in the solar system, but possibly in the galaxy. It is the quietest place in the inner solar system for radio frequencies, because Earth is permanently below the horizon. The moon's body blocks radio interference from Earth, our satellites, GPS, internet, military systems, and all human-generated electromagnetic noise. Solar radio emission is shielded when the far side is in lunar night. For radio astronomers, this means the far side is a dream, a natural observatory, so quiet that it borders on impossible to replicate artificially. NASA, ESA, and CNSA have long considered building low-frequency radio telescopes, dipole antenna networks, interferometers, and lunar surface observatories, because these instruments could listen to signals that cannot penetrate Earth's ionosphere, signals from the cosmic dark ages, the period before the first stars ignited. In other words, the far side is the one place where humanity could detect the universe before light existed. No other world we've landed on offers anything comparable. Tidal isolation and thermal extremes. Without Earth's glow, the far side experiences thermal extremes sharper than the side we see. Daytime, up to 127 degrees Celsius. Nighttime, down to 173 degrees Celsius. These swings drive microfractures in surface rock, expanding and contracting over billions of years. Because the far side's terrain is already older and harder, this thermal cycling has carved some of the most complex regolith in the solar system. The far side's night is especially profound. On the near side, Earthlight softens the darkness. On the far side, midnight is absolute. Only starlight touches the surface. A flashlight dropped onto the ground casts a sharp, almost cruel shadow. There is no air to scatter the beam, no atmospheric haze, no reflected horizon glow. It's darkness in its purest physical form. Cosmic impacts, the story carved in craters. If one single feature defines the far side, it is craters, impact, scars layered upon one another so densely that many are indistinguishable. The most dramatic of all is the South Pole, Aitken Basin, one of the largest impact structures in the entire solar system, 2,500 kilometers across, 8-10 kilometers deep, older than nearly every surface feature on Earth. This basin may have excavated material from the moon's lower crust or even upper mantle, something no volcanic activity on the near side has ever accomplished. When NASA, and international teams analyze samples and spectral data from this region. They are effectively examining the moon's interior without drilling a single meter. The far-side records impact so ancient, they come from an era before Earth stabilized its oceans. It is not simply older, it is a museum of the solar system's violent youth. The human exploration problem. Despite its importance, the far side is incredibly difficult for human or robotic missions. Why? Because there is no direct communication line with Earth. All signals must be relayed through an orbiting satellite. China's Qiqiao relay system made history by enabling the Chang'e 4 mission to land on the far side, the first soft landing on that hemisphere in human history. Future missions will require relay satellites, GPS-like lunar networks, autonomous rovers, AI-driven scientific instruments. Exploring the far side is not just a scientific challenge, it's a technological frontier, the far side as a time capsule. Ultimately, the far side is what the moon truly is when Earth's influence is removed. No Earthlight, no volcanic resurfacing, no radio noise, no gravitational thinning of the crust, no familiar face. It is the moon in its raw state, ancient, untouched, and revealing. And as we cross this hemisphere in our journey, the conclusion becomes clear. To understand the history of the moon, you must look at the side that has never looked back. Chapter 7: The Moon Quakes in the Darkness. If there is one thing that shatters the illusion of the moon as a silent, frozen world, it is this. The moon shakes, not with the brief, sharp tremors we know on Earth, but with quakes so persistent and haunting that scientists once described them as bells that never stop ringing. On the far side, permanently hidden from Earth, these moonquakes take on a character that is even more dramatic, more revealing, and more alien than anywhere else on the lunar surface. To understand them, we must return to a fundamental truth. The moon is not geologically dead. It is slow, quiet, but still evolving, still responding to forces both internal and cosmic. And nowhere is this more evident than in the deep seismic murmurs beneath its unseen hemisphere. 1. The seismic network that heard the moon's heartbeat. Between 1969 and 1977, the Apollo missions placed seismometers on the near side of the moon, none on the far side. The darkness beyond Earth's view remained unmonitored, yet Apollo's instruments still found clues that pointed to powerful activity on the hidden hemisphere. Apollo seismometers detected 4 types of moonquakes. 1. Deep moonquakes, originating to 700-1,200 kilometers below the surface, repeating with clockwork precision every 27.2 days, the exact length of the moon's orbital period. These quakes are triggered by tidal flexing as Earth's gravity kneads the lunar interior, and this is key. The far side experiences stronger tidal strain because of the moon's asymmetrical crust thickness. The far side crust is twice as thick as the near side, amplifying stress deep below. 2. Shallow moonquakes. These are the dangerous ones. They can reach magnitudes of 5.5 and last for 20 minutes straight, far longer than the most violent quakes on Earth. Some signatures suggest that many of the strongest events originated from regions toward the far side. 3. Thermal quakes. As the lunar dawn sweeps across the surface, a transition from 170 degrees Celsius to plus 120 degrees Celsius, rocks expand violently. On the far side, which endures 2 weeks of uninterrupted darkness, The thermal shock at sunrise is even more extreme. 4. Meteor impacts. With no atmospheric protection, the moon is a constant target, but the far side, facing away from Earth, which acts as a partial shield, absorbs a higher rate of high-velocity micrometeoroid strikes. Each type of quake tells a different story, but together they reveal a moon still ringing from its birth, its orbit, and the ceaseless bombardment of space. 2. The far side's crust, a geological paradox. One of the greatest lunar mysteries is the crustal asymmetry. Near side crust, to 30-40 kilometers thick, far side crust, to 60-80 kilometers thick. Why would one hemisphere be so fundamentally different? One leading theory is the companion moon hypothesis. In the early chaos of the solar system, Earth may have had two moons. When the smaller one spiraled inward and collided with the larger one, the impact material accumulated on one side, creating the far side's thick, mountainous crust. If true, the far side is not just the dark side. It is the scarred side, the geological archive of a cosmic collision lost to deep time. And a thick crust behaves differently under tidal stress. It cracks less, but strains more, focusing tectonic stress deeper underground. This leads to powerful deep source quakes that may travel through the crust in long, ringing reverberations. In darkness, beneath an unbroken canvas of ancient highlands, the far side quakes tell a story the near side cannot. 3. Tidal forces that twist the moon from within. Though the moon is tidally locked, with the same face always turned to Earth, it is far from still. Earth's gravity stretches and compresses the lunar interior every orbit. The near side feels this pull differently because it is slightly closer, slightly thinner, and warmer from ancient volcanic flows. The far side, colder and more rigid, behaves like a stressed metal plate. It flexes less. It fractures deeper, and when it slips, it releases energy in long, low-frequency reverberations. Computer models show that tidal strain focuses into deep mantle zones beneath the far side, suggesting that the hidden hemisphere may be where the most intense internal activity originates, even if our seismometers never sat there to hear it directly. 4. The moon as a bell. Why quakes echo for so long? A shallow quake on Earth might last seconds. On the moon, the same energy can resonate for tens of minutes. This ringing occurs because there is no water in the rocks to dampen the energy. The moon's crust is old, brittle, and dry. Its internal structure reflects seismic waves cleanly. Now imagine this phenomenon occurring beneath the far side. A thick crust, colder interior, and deeper tectonic stress. The far side could produce echoes that reverberate through the entire lunar body, like a bell struck at its base. Some Apollo recordings show wave patterns so long and pure that geologists initially thought the equipment was malfunctioning. It wasn't. The moon was singing. 5. The far side's violent meteoric past. The largest and oldest lunar impacts, some spanning thousands of kilometers, exist on the far side. These colossal basins include South Pole, Aitken Basin, 2,500 kilometers wide, Korolev Basin, Hertzsprung Basin. These impacts shattered the crust, created deep fractures, and left behind weakened seismic zones that still respond to tidal stress billions of years later. When a deep moonquake propagates upward in these regions, It doesn't simply dissipate, it resonates across ancient fault lines like vibrations running along the ribs of an ancient instrument. 6. What the far-side moonquakes tell us. Moonquakes matter for more than curiosity. As humanity plans to build radio observatories and Artemis-era habitats on the far side, the seismic behavior of this region becomes critical. From decades of seismic study and modeling, researchers believe the far side likely hosts the most intense deep moonquake focus regions. Its crust may be more stable against shallow breakage, but more prone to deep, resonant events. Thermal quakes are probably more violent due to extreme temperature swings. The thick crust acts as a seismic amplifier, not a damper. In other words, the far side is quieter on the surface but louder deep within, a paradox worthy of a world we never see. 7. A hemisphere that still breathes in silence. Though the far side is locked in darkness unreachable by Earth's direct radio signals, shielded from our view, it is not dead. It breathes, it heaves, it whispers in quakes that ripple through rock older than any life on Earth, and deep under that ancient crust, in the mantle and core, the stresses that shape the lunar interior continue their slow, inexorable cycle. In this way, the far side is not simply the dark side, it is the living side, where the moon's inner heartbeat is strongest. Chapter 8. The Radio Silent Frontier. Why the far side became humanity's quietest observatory. If the moon had a single place that could be described as the quietest point in the entire inner solar system, it would be the far side. After traveling with us through its hidden geology, its unbroken craters, and the scars left by cosmic bombardment, we now arrive at one of the most scientifically precious qualities of the dark hemisphere, its near-perfect radio silence. It is a silence so complete, so stable, and so shielded from Earth's interference that space agencies consider it one of the most valuable natural laboratories available in the solar system. A place where signals from the early universe might still be detectable, a place where the static of human civilization finally fades away. And so, as we move forward from Chapter 7, where we explored how the moon's far side shaped its geology through isolation, Chapter 8 shows us a different kind of isolation, the isolation of electromagnetic quiet. This is more than emptiness. It is a resource, a scientific treasure, and perhaps one of the most important reasons humanity will one day build permanent instruments on the side of the moon we never see. 1. A hemisphere hidden behind stone. To understand why the far side is silent, we must first understand the physics of shielding. The moon is tidally locked to Earth, meaning one hemisphere always faces us. As Earth rotates, the moon acts like a fixed barrier. Every radio wave produced by our planet, from Wi-Fi routers to aircraft radar, GPS satellites, military transmissions, radio towers, broadband networks, and even faint background leakage from communication infrastructure, is effectively blocked by 1,700 kilometers of solid lunar rock. This is not partial shielding. This is total blockage. Earth is the loudest radio source in the solar system after the Sunday. Its electromagnetic noise floods space in all directions so intensely that satellites must use sophisticated filters just to operate. But on the far side of the moon, that noise simply never arrives. It is the only place in the inner solar system where Earth's electromagnetic presence becomes completely silent. For astronomers, that silence is priceless. 2. The universe before stars, the 21-centimeter dream. Why is silence so desirable? because some of the most valuable scientific signals in the universe are also the faintest. Scientists believe that the far side of the moon may be the perfect location to detect the 21-centimeter hydrogen line from the dark ages of the universe, the time before the first stars formed, when the universe was dominated by cold, neutral hydrogen gas. These signals are extremely low frequency, fragile, and easily overwhelmed. On Earth, they are buried beneath radio station broadcasts, plasma noise in the ionosphere, modern telecommunications, electrical interference, reflections from the surface. Even satellites orbiting Earth struggle to detect this faint cosmological whisper. But the far side of the moon, it has no atmosphere, no ionosphere, no human signals, no reflection paths back to Earth. It is the closest thing humanity has to a natural radio observatory, untouched and pristine. Many cosmologists believe that once a low-frequency interferometer is built there, we could detect signals from the universe's first atoms, the formation of the first stars, early galaxy clustering, the heating of the intergalactic medium, the moment the universe transitioned into the cosmic dawn. The far side could allow us to hear the oldest story in the universe, the story written long before Earth formed. 3. Why radio silence matters in modern science. Every scientific instrument has a noise floor, the lowest signal strength it can meaningfully detect. On Earth, our noise floor is extremely high because of human civilization. The far side reduces this noise floor by factors of billions. Radio astronomers describe it like suddenly being able to hear the footstep of a single insect inside a stadium filled with jet engines. Several types of research would become newly possible. Low-frequency cosmology. Signals from the early universe drop below 30 megahertz as a range Earth cannot observe due to ionospheric interference. Detection of exoplanet magnetic fields. Planets around other stars may produce faint radio emissions through auroral processes. Detecting them could reveal atmospheres, magnetospheres, and even habitability. Mapping cosmic rays and plasma waves. The far side's quiet environment allows instruments to detect fine structure in solar and interstellar plasma, searching for extraterrestrial techno-signatures. If advanced civilizations broadcast at frequencies drowned out on Earth, the far side may be the only place we can hear them. The importance of this research cannot be overstated. The far side is not just quiet. It is the quietest location accessible without leaving the solar system. 4. The shielding effect of lunar rock. Lunar regolith and bedrock absorb and scatter radio waves with high efficiency. A rough analogy. 1 meter of lunar soil blocks almost all high-frequency interference. 10 meters blocks nearly everything. 100 meters is equivalent to a perfect radio shield. The entire far side is effectively under a global dome of electromagnetic insulation. There is no place on Earth where such silence exists. Not in deserts, not in polar regions, not under oceans, not underground. Only the far side of the moon, a hemisphere shielded forever by its locked rotation, provides such isolation. A silence created not by luck but by orbital mechanics. 5. China's Chang'e 4. The first visitor to the silent hemisphere. In 2019, China's Chang'e 4 mission became the first spacecraft to land on the far side of the moon. Because direct communication with Earth is impossible from there, China deployed a special relay satellite Kueqiao, positioned at the Earth-Moon L2 point. Among Chang'e 4's scientific payloads was a low-frequency radio experiment designed specifically to test the electromagnetic environment. The results were astonishing. The far side was quieter than even the most optimistic models. No detectable interference from Earth, no ionospheric distortion, no reflected background scatter. It was a radio astronomer's paradise. This verification cracked open a new era of lunar science. NASA, ESA, CNSA, and private groups began designing proposals for lunar dipole arrays, crater-based radio telescopes, interferometer networks spanning several kilometers, surface-mounted LOFAR style systems, deep regolith-shielded receivers. Humanity finally had confirmation. The far side of the moon is the ideal listening post for the universe. 6. Craters that could become telescopes. Several lunar craters on the far side are nearly perfect candidates for future observatories. Their natural bowl shapes allow large interferometers to be deployed with minimal engineering. Most notable is Daedalus Crater, a 9.3-kilometer wide basin with tall inner walls that block even more stray signals and solar noise. Inside a crater like this, a telescope could listen to cosmic background structures, planetary auroral emissions, solar storms interacting with deep space, unknown low-frequency astrophysical phenomena. Some proposals envision stretching ultra-lightweight antenna mesh across an entire crater, turning it into a giant, natural observatory, similar to a lunar version of the Arecibo telescope but immune to Earth's interference. Others suggest deploying hundreds of small modular antennas across the regolith to create a massive phased array. However it happens, the message is clear. The far side is not just a place. It is an opportunity, one unmatched anywhere else. 7. The dark side's scientific destiny. Whether in 10 years or 50, humanity will build its first true cosmic listening installation on the far side. The scientific potential is overwhelming, and no alternative exists. As we move toward Chapter 9, we will examine how future lunar bases, scientific, industrial, or even civilian, could change our relationship with Earth's silent hemisphere. But first, we must understand one final reality. The far side of the moon is not just quiet because Earth cannot reach it. It is quiet because the universe has been waiting for us to listen. Chapter 9. The lunar far side as a cosmic observatory. For more than half a century, scientists have quietly regarded the far side of the moon as one of the most valuable pieces of real estate in the entire solar system, not because of its minerals or its potential for lunar bases or even its dramatic crater fields, but because of something far more elusive: silence. A silence so complete, so unbroken, so perfectly shielded from Earth's electromagnetic noise that it has no equivalent anywhere else in our celestial neighborhood. To understand why the far side of the moon fascinates astronomers on such a deep level, we must shift from geology and orbital mechanics to something more fundamental: the universe's earliest light, the faintest radio whispers, and the signals that Earth can never hear on its own surface. The far side of the moon isn't just hidden from Earth's view, it is hidden from Earth's interference. For the first time in this documentary, we're no longer looking at the moon as a world shaped by impacts or locked in gravitational rhythms. We're looking at it as a shield, a barrier, and ultimately a gateway. A gateway to the oldest chapter of the universe. 1. The quietest place in the inner solar system. Earth is loud, not audibly, but electromagnetically. Our televisions, satellites, power grids, radio networks, military radars, GPS constellations, phone towers, even household electronics constantly leak a haze of radio noise. This blanket of interference, known as radio frequency interference, RFI, forms a noisy fog that prevents astronomers from detecting the faintest signals coming from deep space. But the moon's far side, permanently turned away from Earth, provides something invaluable: a natural, planetary scale radio shield. The moon's solid body blocks terrestrial radio waves, atmospheric reflections, electromagnetic pollution, ionospheric distortion. When the moon drifts between Earth and the Sun during certain phases, the far side becomes the most radio-silent environment anywhere within millions of kilometers. For cosmologists, it is the perfect blank slate. 2. The search for the cosmic dark ages. Before the first stars ignited, before galaxies assembled, before light filled the cosmos, the universe existed in a long, mysterious phase that scientists call the Dark Ages, roughly 380,000 to 100 million years after the Big Bang. No visible light, no stars, no stellar radiation, only cooling hydrogen gas, slowly forming the seeds of structure. The only detectable signal from this era is the ultra-faint 21-centimeter hydrogen line, a radio emission produced when the spins of electrons in neutral hydrogen flip orientation. This signal has traveled for over 13 billion years. By the time it reaches Earth, it's incredibly weak, drowned in noise, impossible to isolate. But on the lunar far side, shielded from all interference, the universe's oldest signal may finally be heard. If humans place radio telescopes there, we may detect the distribution of the earliest matter, the birthplaces of the first galaxies, clues to dark matter, and the universe's initial conditions after the Big Bang. The far side of the moon might be the only place in the solar system where the true cosmic dawn can be observed without distortion. 3. Why the far side is a radio astronomer's dream. No ionosphere. Earth's ionosphere reflects low-frequency radio waves, blocking observations below to 10 megahertz. The moon has no such layer, nothing to block or distort incoming signals. Constant stability. No weather, no wind, no atmosphere. A telescope remains stable for years, with minimal environmental noise. Geologic depressions. Large lunar basins like the South Pole Aitken Basin provide natural cradles for enormous telescope arrays. Thermal extremes. While harsh for humans, the long lunar night to 14 Earth days creates stable thermal conditions ideal for sensitive equipment. The far side is not merely advantageous, it is unmatched. 4. China's future plans and the race toward a lunar observatory. In 2019, China's Chang'e 4 became the first mission to land on the far side of the moon. It brought the Kuijiao relay satellite to allow communication because the far side cannot transmit signals directly to Earth. This mission paved the way for more ambitious concepts. Low-frequency radio telescope arrays laid directly on the regolith, a moon-based cosmic dark ages explorer. The LCRT Lunar Crater Radio Telescope, a proposed 1-kilometer dish built inside a lunar crater. NASA has its own proposals, including the far side array and interferometry networks spanning kilometers. All share one goal: use the moon's silence to hear the universe's first whispers. 5. A new era of lunar science. If built, far side radio observatories could reveal the first stars, primordial black holes, variations in the early cosmic structure, the influence of dark matter on hydrogen, the timeline of cosmic reionization, the physics behind inflation. They could detect space weather patterns, map the solar system's radio environment, and serve as early warning systems for solar storms. This is not just lunar science. It is cosmology, astrophysics, particle physics, and planetary science intersecting in one place. A place that Earth has never seen and barely understood. 6. The Moon as a gateway to the universe's origin. What we've learned so far in this documentary has been rooted in geology, orbit dynamics, and the long history of the Moon's evolution. But here, on the far side, the Moon becomes something different. A lens, magnifying the universe's past. A shield, protecting fragile signals. A platform, ready for the next generation of cosmic discovery. This chapter expands the Moon's role from a silent companion of Earth to an essential tool for understanding the universe itself. Chapter 10. The Future of Lunar Exploration, Mapping the Permanently Hidden World. For more than half a century, the far side of the Moon has remained one of the most scientifically compelling and logistically difficult regions in the inner solar system. It is a realm shaped by deep time impacts, long-dead volcanic activity, and a silence uninterrupted for billions of years. As humanity prepares to return to the Moon in a permanent capacity, the far side is transitioning from an object of speculation into a domain of active exploration. Chapter 10 examines the technologies, missions, and scientific goals that will define the next century of lunar research and why the far side may become one of the most important scientific outposts in human history. 1. The Artemis Era, a permanent return to the Moon. NASA's Artemis program marks the beginning of a new lunar era. While the Apollo missions were brief expeditions, Artemis aims to establish a sustained human presence, including surface habitats, communication systems, and scientific infrastructure. Most significantly, Artemis opens the possibility of placing long-term observatories on the far side, something Apollo never attempted. The far side's scientific value rests on two core advantages: radio quietness. Earth constantly emits radio noise from communication satellites, radar, navigation signals, and countless technological sources. But the Moon's bulk acts as a 2,000-mile thick radio shield, blocking all terrestrial interference. This makes the far side the quietest radio environment in the inner solar system, ideal for low-frequency radio telescopes, cosmic dawn studies, mapping hydrogen from the early universe, detecting faint interstellar emissions. These signals cannot be measured from Earth, nor from Earth-orbiting satellites. Only the far side is quiet enough. Undisturbed geology. Because it never faces Earth, the far side has fewer tidal stresses, older surface regions, little volcanic resurfacing, preserved ancient impact basins. This makes it a geological archive unmatched anywhere else nearby. 2. China's Chang'e program, leading the far side frontier. China became the first nation to land on the far side with Chang'e 4 inches 2019, a scientific breakthrough requiring a relay satellite at Earth-Moon L2 to transmit data. Chang'e 4 revealed thicker lunar crust on the far side, materials excavated from deep lunar layers, unusual rock compositions, a surface shaped by billion-year bombardment. Chang'e 6, Chang'e 7, and Chang'e 8 are planned to explore the far side further, including sample return missions, underground ice prospecting, building blocks for a joint international research base. For the first time, multiple nations are preparing to build permanent infrastructure on a world we have barely begun to understand. 3. The Far Side Radio Observatory, listening to the universe's first light. The most ambitious scientific proposal for the far side is the Lunar Crater Radio Telescope, LCRT, a kilometer-scale radio dish deployed inside a natural crater by autonomous robots. This observatory could detect radio waves from the cosmic dark ages, the era before the first stars formed, more than 13 billion years ago. Today, these frequencies are blocked or drowned out by Earth. The far side is the only place in the inner solar system where the moon blocks Earth's radio waves. The sun can be shielded during lunar night. Long radio wavelengths can be measured without interference. If built, LCRT would become the largest filled aperture radio telescope ever created, the most sensitive low-frequency radio instrument in human history, a window into the universe's earliest structure formation. In a single generation, the far side could transform cosmology. 4. The search for water and volatiles in permanent shadow. Near the south polar far side, many craters lie in permanent darkness, never touched by sunlight for billions of years. Temperatures can fall below 240 degrees Celsius, cold enough to freeze volatiles delivered by comets. These craters likely contain frozen water, carbon compounds, nitrogen, hydrogen-bearing minerals. Discovering and mining this ice would be revolutionary. It can be split into oxygen and hydrogen. It could supply breathable air. It could provide rocket fuel. It could sustain lunar habitats. The far side may hold resources that enable long-term human survival and deep space exploration. 5. Understanding the moon's ancient magnetic past. Unlike Earth, the moon no longer has a global magnetic field, but magnetic anomalies, fossil remnants of the ancient lunar dynamo, are particularly strong on the far side. These anomalies help scientists study how early planetary cores cooled, how early magnetic fields protected atmospheres, the evolution of small terrestrial bodies. The far side may hold the key to understanding why Earth retained its magnetic field while the moon lost its own. 6. Seismic networks, listening to a quieter moon. Because the far side is shielded from Earth's gravitational asymmetries and mechanical noise, it is ideal for deep moonquake sensors, internal structure mapping, mantle core boundary studies, meteoroid impact monitoring. A network of far-side seismometers could reveal the moon's true core composition, heat, flow patterns, the extent of residual volcanic plumbing systems, how the crust differs between near and far hemispheres. In effect, the far side may complete the geophysical map Apollo began. 7. Sample return missions, time capsules of the early solar system. The far side's highlands contain some of the oldest untouched materials in the inner solar system, older than most Earth rocks, older than Mars's accessible crust, older than any asteroid sample we have retrieved. Collecting samples from South Pole Aitken Basin, Vinson Crater, Apollo Basin, Von Karman Crater would allow scientists to determine the moon's early crustal chemistry, the intensity of ancient meteor bombardment, the earliest expansion of the lunar interior, the timeline of solar system formation. These samples could rewrite everything we know about planetary evolution. 8. Lunar habitats. Why the far side may host the first true moon base. While most space agencies target the lunar south pole, many scientists believe the far side is better suited for scientific outposts. Advantages include radio silence, geological diversity, stable terrain, isolation from Earth interference, proximity to permanently shadowed regions. A human base here could become a radio astronomy hub, a seismic research center, a geology field station, a resource extraction site. For the first time, the far side may host a human presence. 9. The far side as a launch pad for deep space missions. Because the far side lacks Earth-facing constraints, it could serve as a staging ground for Mars missions, deep space telescopes, asteroid interceptors, interstellar probes, huge radio antennas, free from Earth noise, could guide spacecraft across the solar system. In the long term, the far side may become a gateway, not just a destination. 10. The far side's new role in human history. As exploration accelerates, the far side transitions from myth to mapping, from hidden hemisphere to scientific frontier. What was once invisible, unreachable, mysterious, is becoming charted, measurable, deeply valuable. The far side is not just a region of the moon. It is a scientific revolution waiting to unfold, a place where human curiosity meets the universe's preserved history, untouched, unlit, unseen. Humanity has looked at the near side for all of recorded history. Now, at last, we are preparing to study the world Earth never sees. The next chapter of lunar science begins here on the silent side of the moon.